understood. They may be useful, either as artifices for calculation, or to assist our understanding by concrete images, to fix the ideas, as we say. They need not therefore be rejected. The hypotheses of the third category are real generalizations. They must be confirmed or invalidated by experiment. Whether verified or condemned, they will always be fruitful. But, for the reasons I have given, they will only be so if they are not too numerous. Origin of mathematical physics. Let us go further and study more closely the conditions which have assisted the development of mathematical physics. We recognize at the outset that the efforts of men of science have always tended to resolve the complex phenomenon given directly by experiment into a very large number of elementary phenomena, and that in three different ways. First, with respect to time. Instead of embracing in its entirety the progressive development of a phenomenon, we simply try to connect each moment with the one immediately preceding. We admit that the present state of the world only depends on the immediate past, without being directly influenced, so to speak, by the recollection of a more distant past. Thanks to this postulate, instead of studying directly the whole succession of phenomena, we may confine ourselves to writing down its differential equation. For the laws of Kepler we substitute the law of Newton. Next, we try to decompose the phenomena in space. What experiment gives us is a confused aggregate of facts spread over a scene of considerable extent. We must try to deduce the elementary phenomenon, which will still be localized in a very small region of space. A few examples perhaps will make my meaning clearer. If we wish to study in all its complexity the distribution of temperature in a cooling solid, we could never do so. This is simply because, if we only reflect that a point in the solid can directly impart some of its heat to a neighboring point, it will immediately impart that heat only to the nearest points, and it is but gradually that the flow of heat will reach other portions of the solid. The elementary phenomenon is the interchange of heat between two contiguous points. It is strictly localized and relatively simple if, as is natural, we admit that it is not influenced by the temperature of the molecules whose distance apart is small. I bend a rod. It takes a very complicated form, the direct investigation of which would be impossible. But I can attack the problem, however, if I notice that its flexure is only the resultant of the deformations of the very small elements of the rod, and that the deformation of each of these elements only depends on the forces which are directly applied to it, and not in the least on those which may be acting on the other elements. In all these examples, which may be increased without difficulty, it is admitted that there is no action at a distance or at great distances. That is a hypothesis. It is not always true, as the law of gravitation proves. It must therefore be verified. If it is confirmed, even approximately, it is valuable, for it helps us to use mathematical physics, at any rate by successive approximations. If it does not stand the test, we must seek something else that is analogous, for there are other means of arriving at the elementary phenomenon. If several bodies act simultaneously, it may happen that their actions are independent, and may be added one to the other, either as vectors or as scalar quantities. The elementary phenomenon is then the action of an isolated body. Or suppose, again, it is a question of small movements, or more generally of small variations, which obey the well-known law of mutual or relative independence. The movement observed will then be decomposed into simple movements, for example, sound into its harmonics, and white light into its monochromatic components. When we have discovered in which direction to seek for the elementary phenomena, by what means may we reach it? First, it will often happen that in order to predict it, or rather in order to predict what is useful to us, it will not be necessary to know its mechanism. The law of great numbers will suffice. Take, for example, the propagation of heat. Each molecule radiates towards its neighbour. We need not inquire according to what law; and if we make any supposition in this respect, it will be an indifferent hypothesis, and therefore useless and unverifiable. In fact, by the action of averages, and thanks to the symmetry of the medium, all differences are levelled, and, whatever the hypothesis may be, the result is always the same. The same feature is presented in the theory of elasticity, and in that of capillarity. The neighbouring molecules attract and repel each other, we need not inquire by what law. It is enough for us that this attraction is sensible at small distances only, and that the molecules are very numerous, that the medium is symmetrical, and we have only to let the law of great numbers come into play. Here again the simplicity of the elementary phenomenon is hidden beneath the complexity of the observable resultant phenomenon. But in its turn this simplicity was only apparent, and disguised a very complex mechanism. Evidently the best means of reaching the elementary phenomenon would be experiment. It would be necessary by experimental artifices to dissociate the complex system which nature offers for our investigations, and carefully to study the elements as dissociated as possible. For example, natural white light would be decomposed into monochromatic lights by the aid of the prism, and into polarized lights by the aid of the polarizer. Unfortunately, that is neither always possible nor always sufficient, and sometimes the mind must run ahead of experiment. I shall only give one example which has always struck me rather forcibly. If I decompose white light, I shall be able to isolate a portion of the spectrum, but however small it may be, it will always be a certain width. In the same way, the natural lights which are called monochromatic give us a very fine array, but a Y which is not, however, infinitely fine. It might be supposed that in the experimental study of the properties of these natural lights, by operating with finer and finer rays, and passing on at last to the limit, so to speak, we should eventually obtain the properties of a rigorously monochromatic light. That would not be accurate. I assume that two rays emanate from the same source, that they are first polarized in planes at right angles, that they are then brought back again to the same plane of polarization, and that we try to obtain interference. If the light were rigorously monochromatic, there would be interference. But with our nearly monochromatic lights there will be no interference, and that however narrow the ray may be. For it to be otherwise, the ray would have to be several million times finer than the finest known rays. Here then we should be led astray by proceeding to the limit. The mind has to run ahead of the experiment, and if it has done so with success, it is because it has allowed itself to be guided by the instinct of simplicity. The knowledge of the elementary fact enables us to state the problem in the form of an equation. It only remains to deduce from it the observable and verifiable complex fact. That is what we call integration, and it is the province of the mathematician. It might be asked why in physical science generalization so readily takes the mathematical form. The reason is now easy to see. It is not only because we have to express numerical laws. It is because the observable phenomenon is due to the superposition of a large number of elementary phenomena which are all similar to each other, and in this way differential equations are quite naturally introduced. It is not enough that each elementary phenomenon should obey simple laws. All those that we have to combine must obey the same law. Then only is the intervention of mathematics of any use. Mathematics teaches us, in fact, to combine like with like. Its object is to divine the result of a combination without having to reconstruct that combination element by element. If we have to repeat the same operation several times, mathematics enables us to avoid this repetition by telling the result beforehand by a kind of induction. This I have explained before in the chapter on mathematical reasoning. But for that purpose all these operations must be similar. In the contrary case, we must evidently make up our minds to working them out in full one after the other, and mathematics will be useless. It is therefore thanks to the approximate homogeneity of the matter studied by physicists that mathematical physics came into existence. In the natural sciences, the following conditions are no longer to be found: homogeneity, relative independence of remote parts, simplicity of the elementary fact. And that is why the student of natural science is compelled to have recourse to other modes of generalization. End of chapter 9.